We're talking about geosynchronous satellites. Do you guys know what these are? Yep.
Satellites that maintain their relative position when
Right. So they remain on the same spot above the Earth. Okay. And they have to be in a special orbit. So okay. So it turns out that. All right. Let me. Do you guys remember the radius of the Earth? What's that? 4,000 miles. Okay, so 6,400 kilometers. Uh, okay. And if you're a satellite orbiting about 36,000 kilometers above, then you would take 24 hours to go around the Earth. Okay? You're late. Right.
The time is passed out by 8 minutes.
So you take 24 hours to go around the Earth. Okay. Now, if you're orbiting 36,000 kilometers above the surface of the Earth, you take 24 hours there. For it doesn't matter what direction you're going, you're taking 24 hours to go around the Earth. Okay. So the only way to remain on the same spot. So, for instance, the Earth is rotating like that. If you go around like this, then you won't remain on the same spot. If you go like that, you won't remain on the same spot. So you had to be directly above the equator and going in the same direction as the Earth is spinning to remain above the same spot. So the geosynchronous satellite orbit is right above the equator. It's 36,000 feet, 36,000 kilometers above the surface of the Earth. Okay. And you're rotating in the same direction as the Earth is spinning. And that is a very special orbit. Why is it special? Yeah.
It's important for communication satellites.
It's very useful for communication satellites. So if you know exactly where a satellite is, then if it's fixed in the sky at that point at all times, you just bounce off signals off of it. Okay. And in fact, so that's one of the most valuable parking spots on Earth. Well, on Earth. Okay. So every country gets allocated a site, and now you can park them. You can park a satellite at about half a degree, every half a degree. So there's 720 parking spots. Yep. And for a given spot, you can have multiple satellites as long as you're communicating at different frequencies and stuff like that. So this is a very valuable spot. All right, so that's a geosynchronous satellite. The orbital speed of the satellite is 3 kilometers per second at that height. And again, okay, so the orbital radius is 42,000 kilometers. The radius of the Earth is 6,000 kilometers, so you're 36,000 kilometers above the surface of the Earth. All right. See, when a satellite is going around the Earth, it is bound to the Earth. It's in a bound orbit. When something is in a bound orbit, its total energy is less than zero. Okay, so here's the kinetic energy of the satellite, and here's the potential energy of the satellite. And the sum of these two is less than zero. So in a bound system, the energy of this object is less than zero. Okay, so a satellite is in a bound motion, is in a bound orbit. Okay. when an satellite is when an object is in a circular orbit, the total energy, which is the kinetic energy plus potential energy, is equal to that. Okay, minus gmm divided by 2r. R is the radius of the orbit. Okay. When you're in an elliptical orbit, uh, the total energy is gmm by 2a. A is the semi-major axis. So this is the semi-major axis, right? So that's the total energy. Okay, do you guys know why you might want an orbit like this? A highly elliptical orbit like that? Yeah. Well, so here's the Earth. Yeah. I don't know if they do it like this anymore, but anyway, so you might need you want an elliptical orbit like this, like that. So when you're close to the surface of the Earth, you can take pictures and spy on things, and then you're far away. And as the Earth is spinning, you get to take pictures of everything. Now, when you're close to the Earth, when you're close, because of friction, you'd be losing energy. So this way, so now you don't suffer friction. So this way, you're extending the lifespan of the satellite. Okay. Yep.
Or you're not losing friction.
Well, the atmosphere gets thinner, and here there's no atmosphere. The atmosphere is very thin, about 100 kilometers. But, all right.
If it's experiencing friction, will it eventually become a circular orbit?
I'm sorry?
If the satellite is experiencing friction,
Mhm.
will it eventually become a circular orbit?
No, its orbit will decay and it'll fall down. No. So in the news, you'll all keep hearing that eventually satellites fall down. And all right. So here's an amazing fact. Just 60 years ago, there were no man-made objects above the planet Earth. Today, so these are the geosynchronous satellites. There's over 500,000 objects circling the Earth. Okay. It's getting crowded. GPS satellites that you rely on all the time, those fly at 12,000 miles above the surface of the Earth, and so on. And Mr. Musk is putting a whole bunch of satellites up there to provide you internet eventually. Okay. All right. What this diagram shows you is that if you're in a bound orbit, that is, if your energy is less than 0, you're either going in a circular orbit around the Earth or the Sun or whatever the central body, or in an elliptical orbit. So all planets go around the Sun in elliptical orbits. If you're in a parabolic orbit, your energy is 0. So this is an unbound orbit. Okay, so for instance, if you go infinitely far away and drop a tennis ball, not directly at Earth, it would go in a parabolic orbit and eventually go back to infinity. Okay. So a parabolic orbit is a 0 energy orbit. And now a hyperbolic orbit is an orbit with energy greater than 0. So to be in a hyperbolic orbit, you would have to be at infinity and then throw the ball with velocity. So you have positive energy. Okay? And that would go in a hyperbolic orbit. Right? You can read all of that. Okay. Now I'll briefly mention about tides. Okay. So the moon causes tides, and Newton explained how tides occur. Okay. So and explaining this part of the bulge was easy. Explaining why is the ocean bulging over here was a little harder. Okay. And so here's how Newton explained this. Okay. So for instance, you wouldn't have tides if these two were point objects. You have tides because these are extended objects. Okay, so here's what's happening. So I'll just make up some numbers here. Okay, so here's the moon. Let's say it's pulling a pound of this material here with the force of 100 units. We'll call it a 1 kg of material is being pulled by a force of 100 newtons. This kg of material is closer to the moon, so it'll be pulled by a stronger force. Let's call it 102 newtons. How about this guy? Less. It'll be 98 newtons. This guy, 101 units. Okay. Now we'll reset 100 newtons to be 0. So this guy is being pulled with 2 newtons in this direction. One Newton. How about this guy? I'm sorry? I'm sorry? -2, very good. 2 units in that direction. And there's your tides. Okay, so effectively the Earth is being pulled away from this ocean. Okay. Anyway, you have tides because the force on this side of the Earth is stronger than this side of the Earth. Okay, so those are the tidal forces, and the difference in this side per pound on this side versus this side, that's the stretching force. Okay, that's the tidal force, and it turns out that you see the tidal force. Even though the sun is exerting a greater force on the earth, so body subjected to tidal force, even though the sun is exerting a greater force on the earth, the tidal force of the sun, that is the differential on either end of this earth, is, you see, half of that of the moon. So the moon's tidal force on earth is twice that of the sun. So it's really the moon that causes the tides, okay, on earth. So for instance, when the moon and the sun line up, then the tides are the highest. So spring tides are the highest, and they can be on either side. So new moon time and full moon time, the tides are the highest. And during neap tide, when the moon is here and the sun is there, the tides are the smallest. Okay. They're working against each other. So the sun is trying to stretch it this way, and the moon is trying to stretch it this way and push it down this way. So this happens to stars as well. If this star is expanding, the gravitational force of this star can pull material apart. If this star expands too much, this material can fall in. So for instance, this here is a picture of a black hole, and material has collected into these in the accretion disk. Okay. So I'm just going to give you a counter example, so you can think about this. Okay. Do you guys know what is the speed, orbital speed of the International Space Station? Yeah, 18,000 miles per hour, 8 kilometers per second. Okay. What is the escape velocity from Earth? Yeah, 11 kilometers. So that's a good number to remember. Okay. So let's say you take a tennis ball, throw it straight at Earth, it'll just fall into the Earth. Okay. You throw it at 5 kilometers a second, even you throw it like that, it'll eventually fall on Earth. You take a tennis ball, throw it at 8 kilometers a second, and it'll orbit. Take a tennis ball, throw it at 12 kilometers a second, it'll just go away. Okay. So you see, if you throw an object at the right speed, it can get caught up in an orbit, in an accretion disk. Okay. You throw it straight in, it'll just fall in. Same thing with a black hole. If the material goes straight into the black hole, it just falls in. But if it's coming at the right speed, it can get caught up in an accretion disk. And then it gets caught up in an accretion disk near the black hole. The gravitational field is strong. So let's say here's a black hole. There's this material going around like that. The force of gravity here is much stronger than on this end. It's getting stretched and it gets very hot. You know? Hot material emits electromagnetic radiation. Okay? And from this radiation, you can get the characteristics of the black hole. You can get its mass and all that. Also, there's a strong magnetic field like that, and there are beams of particles that will escape there, and light will escape there. So around the black hole, you'll have these jets of radiation. Okay. Somebody had a question? Yeah. Mm-hmm.
Yeah, so it's for an object to get caught
In the accretion disk.
It's just the speed, or was it?
Right. You have to have the right speed. I mean, so the International Space Station is not falling because it's going at 8 kilometers. That's the orbital speed. Okay, so we'll briefly talk about Einstein's general theory of relativity. So this is the equation he's most famous for, this little equation. You know? What this equation tells you is, this term tells you how matter and energy is distributed. This term. And these terms tell you how space-time is curved. Okay. Now, let me give you a little example. So, the Earth is going around the sun, of course. Now let's imagine the following. Let's say you go home and make the sun vanish. Flip a switch and make the sun vanish. What will happen to the Earth?
For 8 minutes, it'll continue on its orbit and then fly out into space.
Yes, so after 8 minutes, it will go in a straight line. Newton couldn't have answered that. So he knew that back then he thought the force was instantaneous, in the sense that, okay, so if you ask Newton the following, let's say instead of making it vanish, you make the sun jiggle. Does the Earth feel it immediately? Newton couldn't have answered that. Okay. So Einstein's theory can answer questions like that. Okay. So now how does Einstein answer this? Okay, like our friend said. So remember space-time, matter, so space-time is flat, and then matter makes space-time curve. So now, if you make the sun vanish, the space-time has to get flat, but it is happening at the speed of light. Okay? So, the Earth is just responding to the curvature here locally. So when the space-time becomes flat here, that's when it goes in a straight line. And that happens after 8 minutes, like our friends. All right? So that's just a little blurb on general relativity. Okay, so this is the escape velocity from an object from that distance. What is the escape velocity from the Earth? 11 kilometers. And so now you know what are the velocities of all satellites going around the Earth? I'm sorry? Less than 11 kilometers. Okay, I guess so, but as you're going further out, your velocity decreases. So it's all less than 11 kilometers. Okay. Now here's the deal. If you take a mass, if you start squeezing this, the escape velocity increases. As the radius gets smaller, the escape velocity increases. And of course, we know that nothing can travel faster than the speed of light. So if you squeeze an object to a radius such that the escape velocity becomes equal to the speed of light, then it's become a black hole. Okay? So for instance, what do you have to do to Earth to make Earth into a black hole? You have to squeeze it to the size of a marble. The sun, the radius of the sun is about 700,000 kilometers. You can look it up. And you can turn the sun into a black hole. Its radius needs to be about 3 kilometers. Okay. So now here's the deal. Let's say you take the sun and you start squeezing it. Okay. You squeeze it past 3 kilometers, it doesn't stop there. The matter keeps falling, and we don't know how to describe it anymore. As far as we know, it'll all fall. If you ask Einstein, he'll say it'll all fall to a point, but even he knew that that's not the final answer, but he doesn't know the right answer. Nobody knows the right answer. So you need a quantum theory of gravity and stuff to explain that. All right, so, okay, if you squeeze this object beyond this point, at this point, the escape velocity has become the speed of light. Okay, so this is called an event horizon because no information from beyond this point can get out there, and information from here can get in there, but information from here cannot get out. Okay, so this is the horizon. Okay. By the way, this radius is called Schwarzschild radius after Mr. Schwarzschild. Okay. And so for the sun, for the Earth, the Schwarzschild radius is about an inch or something like that. For the sun, it's about 3 kilometers. Okay. In nature, stars will evolve, and if the mass after they die is greater, this is the mass of the sun, which is 2 times 10 to the 30 kgs. If the mass of the star after it dies is greater than 3 solar mass, it'll become a black hole. Okay. So here's a black hole with an accretion disk, and there's jets of material material in the accretion disk is at extremely high temperatures, and it'll emit radiation in the X-ray region. So here's a Hubble Space Telescope picture of a jet from a black hole. So this is a supermassive black hole. And again, at the centers of most galaxies, so at the center of our Milky Way galaxy, there's supposed to be a 400 million solar masses black hole. And this is how we discovered it. Okay, so you guys remember the period square, if you're orbiting a central mass, the period, the time it takes to go around divided by radius cube is proportional to the, inversely proportional to the central mass. Greater the mass, smaller the period. Okay. So scientists have observed these stars going around an object that is invisible, and they're going extremely fast. Massive stars are going at 50% the speed of light, and so that's an indication of the presence of solar masses. So 4 million solar mass resides at the center. All right. So here's an interesting phenomenon: gravitational lensing. See, here's a picture. You see, these are two objects in this picture. It turns out that they're the same objects. How do we know they're the same object? What's that? Well, 200-watt bulbs are the same amount of light. Yeah. You see this picture, right? What does that look to you? Two objects? This is one object, that's all. But we believe it's the same object. So what you do is, you look at the intensity of light versus wavelength, okay, coming from those two objects. It's exactly the same spectrum. They are the same object. Okay. So what's going on? So here is what's going on. Einstein had predicted with his theory that so if there was a star here, light coming from here, gravity would bend the light. Okay, and this was one of the predictions of Einstein that we first measured. Okay, and see, you're hardwired to think that light travels in a straight line, so this star would appear there in the sky. Anyway, that's what's happening. Quasars are extremely bright objects. They're the brightest objects out there. They're massive black holes eating up stuff, and light from there, see, this intervening mass bent the light, and there's the image that was formed. Here was an image that was formed, and that's what's happening. So the intervening mass is lensing, and you're seeing images of this object. Okay. So So here's the composition of the universe. Okay. 70% dark energy, 25% dark matter, and 4% normal matter. Okay. Again, we don't know the nature of this energy, we don't know the nature of this matter, and that's why we call it. Well, how do we know that this matter exists? Okay. So we've had evidence for this for a long time. So here's one of the pictures. Okay. Okay, so you see this equation, if you're orbiting, if you're going around this guy, the gravitational force of this guy is providing you the centripetal force. There's the centripetal force, and this mass is providing the gravitational force of this mass is providing the centripetal force. Okay, so the speed of this guy, as you go further and further out, falls off as 1 over square root of r. So the orbital speed of this guy falls off as 1 over r. Okay, so here's a galaxy, and we're looking at the orbital speed of all these stars. Okay, so these are all the visible stars you can see. There's no more stars here. So as you are finding the orbital speed of these guys, there's no more mass here. The orbital speed should fall off as 1 over r, square root of r. The orbital speed should fall off. But look at this. The orbital speed is constant. That must mean that there's mass over here that you can't see. And this is an old graph. So there's dark matter out there. So for every pound of normal matter, every pound of normal coffee, there's 5 pounds of dark matter coffee out there. Yeah. So here's a computer simulation. All the blue stuff is dark matter. Okay. So unseen matter producing gravitational lensing effect is all right. Now in the next 30 seconds, I'll tell you one of the greatest experimental results in the last few years. The detection of gravitational waves. We first detected them in 2015. This is absolutely amazing. Okay, so if you want to emit electromagnetic waves, what you want to do is you want to accelerate a charged particle. So you can grab hold of a proton or an electron and jiggle it, and it'll emit electromagnetic waves. Okay, so grab hold of an electron, which is what a dipole antenna will do. Jiggle an electron like that, and it'll emit electromagnetic waves. You want to emit gravitational waves, do the same thing with your hands. Except that those waves are very weak. You want to be able to detect the gravitational waves, you have to jiggle a larger object. What do you mean by a larger object? A black hole. How do you jiggle a black hole? What's that? I'm sorry? Yeah. Recruit another black hole. Okay, so that's what, if 2 black holes are going around each other, they're strong gravity, they're jiggling. Remember, circular motion is 2 harmonic oscillator motion. Okay? So 2 black holes going around each other, okay, they're emitting gravitational waves. I'll tell you these numbers, you'll have to think about them. It's just mind-boggling. Now this kind of stuff happens all the time. we've only detected it now. So, I mean, these are, by the way, binary star systems are quite common and stuff like that. So they're going around each other, they're losing energy, and they're getting close together and stuff like that. So they've been orbiting around each other for millions of years and stuff. And these two black holes were orbiting each other, and in the last 200 milliseconds, we were able to detect the gravitational waves. Only then was the gravitational wave strong enough for us to detect it. You know? So, all right, so now we'll look at the numbers. So, first direct observation of gravitational waves was made in 2015. So you see here's 0.25 seconds to 0.45 seconds. So these black holes had been orbiting each other for millions of years. We were able to observe it in the last 200 milliseconds. That's when they were radiating the most energy. And we were able to barely detect it in the last 200 milliseconds. Okay. How much energy were they radiating? So, okay. In the last 200 milliseconds, the amount of energy being radiated into the gravitational wave just by these two guys were about 100 times that of all the stars in the observable universe. So take the light coming from all the stars in the observable universe. So these two objects were radiating in gravitational waves 100 times that energy in the last 200 milliseconds. And we were barely able to see that. All right. So, what happens when gravitational waves pass you? Okay. Here's I'll tell you more about, I guess. So, what happens? How do we detect these guys? Okay. So, when gravitational waves, so if you have, let's say you have a circle of masses like this, when gravitational waves pass this circle by, they'll stretch like that. So this is a quarter cycle, then it go back to a circle, then it'll stretch in this direction, then go back to a circle, and so on. So okay, here, this. Okay, so here's how you detect them. Okay, and how much is this stretch? Okay, so this is highly exaggerated. So this circle becomes like that. And when this event happened, the strain was 10 to the minus 21 meters. So if the radius was 1 meter, this distance was 1 meter plus 10 to the minus 21 meters. Do you guys remember the size of an atom? 10 to the minus 10 meters. The size of a nucleus, 10 to the minus 15 meters. So this 1 meter stretched by 10 to the minus 21 meters. All right, so to put this in perspective, the distance from the Earth to the sun, what is the distance from the Earth to the sun?
93 million miles.
I'm sorry?
93 million miles.
93 million miles. That stretched by the width of an atom. And we measured them. Yep. I'm sorry? No, well, I'll show you in a second. Imagine that. The distance from here to the sun stretched by the size of an atom. So how did we detect it? Yeah.
How do you get rid of the interference?
Oh, there you go. All right, good questions. Yeah. All right, so how do you detect something so sensitively? Okay, so here's what you do. You use a light beam. This is a beam splitter. You make half the beam go this way, reflects off a mirror, comes back here, and here's a beam. This mirror beam goes there and comes back here. And what you do is you make the two beams come by such that when one beam comes with a crest, the other beam comes with a trough. And you make the beams exactly cancel each other. Now, if a gravitational wave goes by, and if this distance stretches, now this beam has traveled extra distance, so now there will be a mismatch. Okay, any slight disturbance will give you a mismatch, and you'll have light there. You know, but if Austin runs by, the ground will shake and there'll be a mismatch. If a truck drives by, there'll be a mismatch. So how do you know a signal from a noise? What's that? So here's what you do. So you spend billions of dollars building this lab. You spend billions of dollars building exactly another lab like that. And if a gravitational wave goes by, you record a signal. And if you record an identical signal there, then you know it's not two trucks. Okay, so now there's a worldwide network of gravitational wave detectors, and we are also building one in space. Okay, so it's pretty amazing. All right, guys, so we will stop here. We'll take a 5-minute break, and then we will